updated.
We got 13 viewers, Roman.
Wow, wow, wow. They're not all me.
One of them is me.
Okay. Ah, perfect. I can see us on YouTube now. That's awesome.
Yay.
Okie dokie. All right, hello everybody. Thank you all for coming. I'm just gonna see it's stable. It's not going down. We are good. Okay. And is the audio good? You guys say something?
Hi.
Okay,
Hello.
that's awesome. All right, perfect. Let's get started then. Thank you everybody for coming to our fall 2020 info session. Sorry about the little delay. Um, so we are Waterloo Rocketry. My name is Roman Kobitz. I am the recovery team lead for Waterloo Rocketry. I am in 2B mechanical engineering, and I'm also one of the co-leads on this, co-leads this year on the team. Jacob, mind introducing yourself there?
Yeah, hi. I'm Jacob Deary. I'm in 4A mechatronics engineering. I'm the software lead for the team.
Hey guys, my name is Shirley. I just finished Mech 3A. I'm one of the co-team leads and also Airframe sub-team lead.
Hi everyone, I'm Ryan. I'm in 2B Mechanical Engineering and I'm on the software team.
Right on. So today we're going to be going through some information about what our team does, who our team is, the sub-teams on our team. Going to talk about some of the components as well of our rocket, and we're going to talk about how you guys can actually get involved. As well, after the formal part of the presentation, we're going to be splitting off into two breakout rooms on a platform called Jitsi. It's similar to Zoom, but you can run it in your web browser. We'll have the links on screen as well for you guys to join that. And what that is, you'll be able to essentially be in a chat room with a lot of our current members, and you can talk to them about anything on the team, technical, non-technical, general questions, things like that. And also, ongoing through the stream, and actually you can see the link on the bottom right there, we have ongoing question rooms in Slido. So yeah, www.sli.do. Type in our room code, WR-info, all caps, and you can actually ask us questions live through the stream, and we will get to all of them at the end of the presentation. So without further ado, let's get going. What is Waterloo Rocketry? Waterloo Rocketry, we're a student design team at the University of Waterloo, of course. We're composed of about 50 undergraduate students, but you know that number is growing all the time. And we're actually open to students from any faculty in the University of Waterloo. It's not only engineering. What we do is we develop and launch high-powered rockets. We do this because we compete annually at the Spaceport America Cup. It's our competition, which we're going to talk a little bit about. The goal of the team, which we will talk about in more detail as well, ultimately is to give students a learning opportunity. So if you're interested in aerospace, if you're interested in mechanical design, electrical design, this is a good place for you.
So the Spaceport America Cup is the biggest rocketry competition in the world for undergraduates. In 2019, over 100 schools from about 15 different countries participated. You can see on the right there the pictures. This is just outside of the convention center with every team. And the Spaceport America Cup is, the main section of it is split up into 6 categories, which are all listed on the screen. 10,000 and 30,000 feet COTS, 10,000 30 feet solid SRAD, 10,000 30,000 feet liquid hybrid SRAD. Now, you don't need to worry too much about the terms. The 10,000 and 30,000 are representing height targets of 10,000 feet and 30,000 feet, and just to the right of it is the engine type. Don't worry about it too much. It's not something you need to know. We'll talk about it later. So next slide, please. So we've competed in the Spaceport America Cup pretty successfully for the past few years. In 2017, we launched VIDAR 3, which was a rocket that had a liquid and hybrid engine, SRAD, which stands for Student Research and Design, which means we built the rocket all on our own. and at a height target of 10,000 feet, we managed to take home first place prize, and we also managed to take home the our first Jim Fafaro Technical Excellence Award. In 2018, we stayed in the same category and made some upgrades for UXO, or Unexploded Ordnance, and we also managed to take home first place. The year after that, we upped our height target from 10,000 feet all the way up to 30,000 feet, still using a liquid hybrid engine, and we managed to take home second place. And unfortunately, last year, the Spaceport America Cup was canceled due to COVID-19. Next slide. So at the Spaceport America Cup, you're judged on many different factors, not just how high your rocket goes, although that is one of the main factors. So apogee refers to the highest point of a rocket during its flight. And the 10,000 or 30,000 feet that we saw earlier are height targets. Now, if you go significantly above this, this is just as bad as if you were to be significantly under it. So not only do you have to meet the height target, but you have to be as precise as possible. So getting 10,300 feet, for example, in the 10,000 category is much, much better than getting like 14,000 feet. We also need to successfully recover our rocket. So what goes up must come down, and it can come down very fast if a proper parachute is not deployed and shatter into thousands of pieces. So the successful recovery and deployment of our parachute, making sure the rocket comes down in one piece, we're judged on this as well. Now, each year, for each rocket, we have to write a project report. Now, this project report is pretty long, dozens and dozens of pages. And in this, we detail every little aspect of our design and development, all the analysis, all our simulations, and the quality and robustness of our rocket. We're judged heavily on this project report and overall just the quality of our engineering on the rocket. Now, SRAD is a term that was used just a few minutes ago, and it stands for Student Research and Design. Now, this is kind of a label that is put onto rockets. You're either SRAD or you're not. And SRAD is when the team fully researches and designs every part of the rocket. Now, many teams at competition use what are called COTS engines, where they kind of buy the engine off, it's called commercial off the shelf. So they buy their engine from a supplier. We like to take on the challenge of designing this all on our own, and we're judged differently for it. And lastly, the most important thing is safety. Of course, with rockets, there could be explosions. The rocket could come back and land on people. This is the number one priority to make sure none of that happens, and we're judged very heavily on it. Next slide. So Shark of the Sky is the last rocket we launched. It's the rocket we built in 2019, and it had a 18-foot length with a 6-inch diameter. It was targeting 30,000 feet, but due to some issues with data relay and field sensing, we only managed to get to 15,568 feet, which is still a pretty good launch, but a bit shy of our target. The fuel we use is a solid fuel, and we use a liquid oxidizer. That's why it's called a hybrid engine, because the state of the fuel and oxidizer are different. The fuel is HTPB, which stands for hydroxyl terminated polybutadiene, and it has an aluminum powder mix. And the oxidizer is nitrous oxide, also known as laughing gas. At peak, the engine produces about 1,300 pound thrust, which gives it a max speed of just short of Mach 1 at 331 meters per second. It has a dry mass of 47 kilograms, which is when the rocket is empty without fuel or payload. And at launch, it has a wet mass of 77.5 kilograms. And just as a fun fact, out of over 100 rockets at Spaceport America Cup 2019, Shark of the Sky stood the tallest. So now I'll hand it off to Shirley to give you a more in-depth view of the rocket.
Yeah. So this is just to give you guys an overview of what sort of systems we have on the rocket, because we will be referring to the different systems we have on the rocket, and this is to help you visualize that. So at the bottom of the rocket, we have the fin can, which is essentially the assembly with the fins. We have the combustion chamber, where all the propulsion magic happens. The feed system, which connects the oxidizer tank to the combustion chamber. So the oxidizer, nitrous oxide, flows through that section once it's time to launch, and we ignite the engine. The oxidizer tank holds the oxidizer. It is both a pressure vessel and also a structural component of our rocket. the vent system. So this system is located at the top, and we use it to vent the system when when we're filling, or if we need to make a launch abort, then we need to vent the system and safe it so that people can approach. The payload is, we will talk a bit more about it, but it is a science experiment, and we have a really interesting one for this year. Recovery system, as we mentioned, this is the system that has everything to do with recovering our rocket safely, bringing it down at a speed that does not cause damage to the rocket. And lastly, at the top, we have the nose cone. So this is a composite part that has a aerodynamically optimized shape to reduce drag. Next slide, please. Okay. So I know I know we talked a bit about our competition, but I don't want you guys to get the impression that winning at competition is our main goal. Competition, you can think of it as a means to an end. It provides challenges, interesting challenges to us, and it gives us the opportunity to learn and apply the theory that we learn in class to real engineering problems. And our engineering problems just have to do with rockets. In addition, once you've started working a bit more with us, you'll find that there's always an emphasis on safety, reliability, and robustness, as well as optimization. So safety, because rockets can be dangerous. When testing, we're working with the potential for explosion, as well as pressurized systems that can be dangerous. Reliability, because our competition happens once every year. We only get one opportunity to launch every year, which is why we do everything in our power to test and to research to make sure that our systems all work at competition. And lastly, optimization, because in order to reach our height targets, we need to make sure that every part of our system is optimized, so we get the most performance for the least weight. And next slide, please. Okay, so next up, we're just going to show you guys two videos. This first video is a test that we did, an engine test that we did in 2018. So go for it.
Current is 500, rising.
On injector valve.
Open injector valve in 5, 4, 3, 2, 1, 0.
Roman, just let me know when you're done playing the video, because there's a bit of a delay between what I'm seeing and what everyone else is seeing. Okay. Next slide, please. Okay, so this second video is our launch at competition in 2018. This was with our rocket UXO. We do have a more recent video for 2019, which is on our YouTube page, but we wanted to show you guys this video because it's got a closer shot and it looks cooler. Go ahead.
Open injector valve in 5, 4, 3,
Next slide, please. All right. So just a quick summary of our flight simulation tool. The flight simulation tool we use is called OpenRocket. I put a picture of sort of the main page of OpenRocket here. OpenRocket gives us data through simulation about various key characteristics of our flight. So one of the most important parameters is stability. Stability is essentially a non-dimensional number that essentially indicates how likely it is that your rocket will flip direction and after launch and come back at you. So this is one of the most important flight safety parameters, and we always need to make sure that the data that we're putting into our open rocket simulation is accurate so that we can ensure that the rocket isn't going to go unstable. Flight dynamics, so open rocket also simulates a variety of parameters for the state of the rocket. So our rocket, it has 6 degrees of freedom, 3 axes about which it can rotate, and 3 directions along which it can translate. And OpenRocket attempts to simulate how the rocket is moving throughout the flight. Lastly, apogee prediction. So as Ryan touched on earlier, apogee prediction is a really important judging criterion for us at competition. And there are a lot of parameters that can affect this. For example, like the weight of the rocket, the weight distribution of the rocket, the aerodynamics of the rocket, and thrust characteristics. And next slide, please. All right, let's start talking a bit about the projects that we have in store for the year. First up, Airframe. So the airframe is just a term we use for the structure of the rocket. This includes the structural members and also the shell of the rocket. So one of the projects that we're working on this year is the Ox Tank Outskirt. So this is essentially a project that allows us better access to a section that has a lot of mechanical components and assemblies that we want to be able to access while the rocket is on the launch tower. So here I have a picture of the CAD. So in this section, this is some CAD for the feed system, which was shown earlier in the sort of diagram of the whole rocket. And this connects the ox tank, the oxidizer tank, which is on your left, to the combustion chamber, which is on your right. And the ox tank outskirt is what goes around this and connects the two sections together. We also have a variety of composite parts that we're working on this year. Roman is showing a old part, which is our Shark of the Sky nose cone. You probably can't see on the inside because it's pretty dark, but this is made of fiberglass, and the team made this part from scratch. So we started off with fiberglass cloth and epoxy. We made a mold for it, and we performed a layup and cured the part so that it would be light and strong. Some other things that we are working on are the fin can, the body tubes, which are essentially the shell of the rocket. They are both structural and have aerodynamic purposes, as well as the fairings, which are non-structural, but help to streamline the section that is shown in the picture. Roman, do you mind? Next slide. Okay, electrical. So the team in the past few years has our electrical subteam has grown significantly. We now have like various systems both onboard and offboard the rocket. So some examples of onboard electrical systems are Rocket CAN, which is essentially uses a CAN protocol for all of our systems, electrical systems that are on board. Our payload has a number of PCBs and electrical systems. Offboard, we have data acquisition, which is really important, especially for testing. We have our remote launch control system, RLCS. This is essentially the system that allows us to launch the rocket at a safe distance. And just to highlight some of the systems that we have on board, in the picture you can see that small board on the left, that's mini sensor board. So that's a board that contains a suite of sensors that will record and log data throughout the flight of the rocket. On the right, you can see a bigger board with a battery strapped to it. That's the vent board, and that was the board that controlled the electromechanical assembly that allowed our oxidizer tank to vent. You can't see it you can't see that assembly because it's on the other side of this mounting plate. And in the back, you can see the oxidizer tank. So lastly, all of our PCBs are designed. Okay, thanks. All of our PCBs are designed by team members. And sorry, PCB stands for printed circuit board. And we will be having tutorials to teach you guys the skills to make your own. Okay, next slide.
All right. Thank you, Shirley. Now I want to talk a little bit about our payload. Shirley mentioned it. We do have separate electrical boards that go in the payload, but what
Roman,
the
you're
payload?
muted.
Roman, you're muted.
I'm not. Oh.
Roman.
Sorry, guys. I have two mute buttons. I was going through on the stream, but not on our calling app. All right.
Oh.
So what the payload is, it's essentially the cargo of our rocket. At competition, we get awarded extra points if we actually have a functional experiment that flies on, and that's what the payload team actually builds. This year, it's really cool. We're doing a particle physics kind of material science experiment. As you can see there, we're analyzing the material properties of boron nitride nanotubes and metal oxide coatings for the SDL payload challenge. And essentially, what that means is that we are testing these two different types of materials, the boron nitride nanotubes and the metal oxide coatings. We're actually testing how well they insulate against ionizing radiation against ionizing radiation. And that's relevant to space because there's a lot more ionizing radiation out in outer space. These and those ionizing radiations can interfere with electrical systems, so it's important to have some sort of protection for them. So yeah, it's a very cool, relevant experiment, and it also lets all our members get hands-on experience doing real science and doing real experiment design. So some of the things that our team actually takes part in is the payload team does is they do the software simulations of detectors to actually make sure that they're going to work correctly and to figure out what they should expect from the detectors if they're working correctly. of course, all the detector hardware and flight computer software. So that's to do with making all of the electrical components to interface with the detectors, and then writing the software to run the detectors and to log all the data for their analysis. And of course, the CubeSat module CAD, which you can see here in the background. CAD just means the the uh, uh, the computer-aided design, so the 3D model of it you can see here, and then we're actually going to be making this or getting this made for flight in our rocket. You can see it consists of mechanical assembly of a lot of aluminum frame pieces to actually house all of the PCBs, and as well as it'll be housing the detectors. The CAD for the detectors isn't in this current model, but you can see on the left, I believe that's the battery module and the flight computer board. And additionally, of course, the payload team is actually going to be at competition when we go to launch the rocket. They're going to be putting in all of their metal oxide samples and their boron nitride samples, and then when we actually get the data from the rocket upon landing, they're going to be compiling all that research, and if there is significant findings, the potential to also write and publish a research paper exists with that as well. It's also for the SDL Payload Challenge, which is like an event that runs alongside the rocketry competition. So teams all send up experiments, and the best experiments that are judged will get some prize money as well associated with it. Next, I'd like to talk about our recovery sub-team. So recovery, as we talked about, is the stage of flight where everything comes back down to Earth. We've flown to 30,000 feet, the engine is burned, the payload is gathering data, and suddenly we're at the top of our flight and we're going to start coming down. Well, we're not going to come down and crash down into the ground and become 2,000 pieces. We're going to deploy our parachutes so that we bring everything down in one piece. Now, in the past, we've been using 2 parachutes, and that's part of a rule in our competition that we have to have 1 small parachute at the top of the flight and 1 large parachute closer to the ground that deploys. This year, really exciting project that we're doing is we're developing a new reefed recovery parachute, and what that should do. What that should do is eliminate essentially one of the parachutes that we have to have inside of the rocket, because the reefed parachute will act as 2. How it will do it is by being constricted to a small shape on deployment, so it'll act as the small parachute, and then it'll be allowed to release and expand to the full size at a lower altitude. Of course, with this, parachutes are really complicated. Aerodynamics is very complicated, and parachutes especially are very hard to simulate and predict. So we're doing a lot of testing on this new parachute system to make sure that we know exactly how it's going to behave when we deploy it in flight. So that's that truck test rig. That's building an actual assembly to mount on top of a pickup truck that we're actually going to be able to deploy some prototype chutes out the side of the pickup truck and get data about the drag characteristics and about the forces that they pull on deployment as well. There's a lot of machining involved with recovery as well. One of the projects is that we're working on our own pyro cutters. These are little metal cylinders with a little pyrotechnic charge inside of them, and what they actually do is they're what we use to deploy the reefed parachute, and they're what we use to actually release the parachute to unconstrict and become big. We're trying to make our own this year. In the past, we've been buying them, but they're quite expensive, and we think that we can give it a shot. So if you're interested in machining that kind of pyrotechnic, want to blow things up, a lot of testing we're going to do with them. That's definitely an interesting project. And of course, all of our bulkheads and our electrical fixtures and stuff. We have to fly altimeters inside of the rocket and telemetry system, and all of that gets housed inside of a separate section called recovery electronics, and we do the structural design and building of it. And you can see one of our co-leads there, Zach. He's standing inside of that big yellow and black parachute. He actually sewed that parachute himself last year. We used it as our main parachute, and hopefully we hope to repurpose it into our reef parachute this year. So if you're interested in sewing, it's also an interesting team to get involved in. We sew our own parachutes, lines, everything like that. Propulsion. So, I mean, some would say, this is really the meat of our rocket. Without the propulsion team, we don't go up. We don't really have a rocket. We kind of have more of a big, pointy paperweight. We have a couple of ongoing projects with the rocket. First, I'm going to talk about the ones that are actually ongoing with our hybrid engine, Kismet. That's the current engine that we are flying on the rocket. You saw UXO going up on Kismet. That was actually Kismet's first flight in that video that you saw of the rocket taking off. There's a couple of really cool projects that we're doing this year. One of the most notable that I have actually right beside me, it's really exciting, is our new nozzle. This is it. It is made out of metal. It is 3D printed metal. It's made out of Inconel 625, which is high heat resistant alloy. And we're going to be testing this out very soon. We got this printed by Lab on Campus called MSAM. They do metal 3D printing. And they quoted us $9,000 for it. They sponsored it. They did it for us for free. So we're really excited to test it out. A lot of really interesting analysis went into this, FEA and thermal analysis. We're actually using a unique cooling solution called two-stage evaporative cooling, where a two-phase evaporative cooling, where we have liquid water inside of the nozzle. We evaporate it. Or it evaporates because of the heat of the engine, and the steam is released out of the vent holes, and that cools the engine down. So, really cool project. That's one of the things that we're working on with Kismet. Another thing is we're making a fill sensing system using a magnet inside of our oxidizer tank. That's to measure the amount of oxidizer that we have inside of the engine while we're filling it, because of course we're not there right beside the rocket filling it. That would be unsafe. It's nitrous oxide is what we're putting in it. So we're remote. So we're doing a remote fill operation, and we need to be able to tell how much oxidizer inside of the ox tank. So that's an exciting project that we're working on this year as well. In addition to that, in addition to all the hybrid engine work that we're doing, we are also currently working on the development of a liquid engine rocket. We already did one test on our liquid engine this past March, and you guys can go check out the video on our YouTube channel. And right now, we're working on a couple of interesting projects. At that last test, we did see an anomaly where we had too much nitrous oxide in the engine when the fuel was put in, and as a result, it did what's called a hard start, and the result was that it did explode. You can see that in the video. I should say everybody was safe, in part due to infrastructure, which I'm going to talk about next. But so we're working on a couple of designs to actually mitigate and to solve the issue that we ran into. So first is the ignition system. In order to actually ignite the rocket, we pass through liquid oxidizer and liquid fuel into the engine, and that passes through the injector, which you can see on the right there in the CAD. It's actually really interesting how it works. I'll quickly describe it. You have these two chambers. One of them is for fuel. That's this green one here. And when the fuel comes in, it's pressurized by nitrogen, and it's sprayed out of these little tiny nozzles at the bottom. This is all going into the combustion chamber, by the way. And then you have nitrous oxide, which comes in through this hole into this orange chamber and comes out of the little slit at the bottom and goes vertically down. So you have the horizontal fuel, or the spray of fuel going horizontally, the spray of nitrous oxide going vertically, And when it mixes, it actually it mixes it really well, and you get this really potent, really kind of energetic mixture of ethanol and nitrous oxide that then when we pass it through the heat source, that's how we get our combustion. And in addition, we're working as well on all the other components of the liquid engine. We have our tanks currently made, but we're building our combustion chamber and nozzle as well that we're going to be using in the tests. Now, infrastructure. I mentioned that we had a test that exploded, and that's where infrastructure comes in. You can see in the picture here, this is our new test site. Now, in the past, we did our tests right outside of the main engineering building here at the University of Waterloo, E5. It was about 20 feet away from the building, not so safe. Now we have a brand new test site, which is in the middle of a field. We bought a shipping container last year, modified it, ripped the floors out, put in metal flooring, put in an engine test stand, put in some hardware to hang our tanks, we put in some hardware to mount our tanks, and put in all of our plumbing system, and then we got it moved out into a big empty field where we can do higher risk engine tests safely. So some of the ongoing projects with our test site are the tank heating system. So we need to keep our oxidizer tank warm during our tests because we're often testing in the winter, but when we go to launch, we're in the desert. So in order to simulate that desert environment, we have traditionally used a hot water jacket around our oxidizer tank to keep it warm. So we need to make a solution for that now that we're out in the middle of a field and don't have access to hot running water. Additionally, we're working on making a stand to actually hang our large oxidizer tank that's used by our hybrid engine. Yep. So I mean, you can actually see. You might be able to see right behind me. There's our large oxidizer tank hanging there, or lying down there on the shelf. So we need to be able to hang that up vertically so we can measure the mass of it while the engine's firing. And otherwise, we are improving our test stand, and we are we're improving the test stand, making modifications to it to get it ready for our next tests. Another infrastructure project, which you saw in that previous video, was actually our launch tower. There are no kind of current ongoing projects with the launch tower, but as we get closer to competition, there are definitely that kind of work to get the launch tower ready for competition 2021 will get underway. And now to Jacob with our tests.
Yeah, thanks, Roman. So we just went over the propulsion system as well as our test infrastructure, and the whole reason that we have this sort of infrastructure is so that we can safely test the engine on the ground. Unfortunately, in Canada, it's very difficult to actually launch a rocket. There's a very long process in order to actually get permission to do that, and so we're unable to do flight tests of our rocket before we bring it down to competition. So we want to make sure that as much as possible, we can test it on the ground, test things in simulation, and run calculations so that we can be very confident that when we get down to New Mexico, we can launch our rocket safely and successfully. The two main tests that we do on our engine on the ground are called cold flow tests and static fire tests. Cold flows are named cold flows because we don't actually fire the engine. In most cases, we will just pressurize it using carbon dioxide or nitrogen instead of our oxidizer, nitrous oxide. Both carbon dioxide and nitrogen are inert, they're non-oxidizing, and we don't need to worry about any risk of explosion or combustion when we're using those. They do, however, in many cases have very similar properties to nitrous oxide in terms of pressure and density, so we can use them to test our pressurized systems, test the fluid dynamics properties of components like the injector, and also go through a full run through of our test procedures to make sure that that we're good to go when we actually want to fire the engine. And that leads us to the second type of test, a static fire. It's called a static fire because we fire the engine, but the engine stays static. It doesn't move. We have it strapped to the test stand that Roman showed earlier, and we have a bunch of sensors mounted around the engine and connected to the plumbing to measure pressures, thrust, mass of propellants. And we use all of that to build a complete model of our engine. And we plug that into OpenRocket, which Shirley showed a bit earlier. And we can use that to simulate our rocket's flight. So these tests are pretty resource intensive. We need to set up the whole test site with the shipping container, with the test stand, with our plumbing system, set up the engine, and then run through it. So it usually does require a lot of people to help out, and takes the full day. So if you're in Waterloo and you're interested in helping out with this, then keep your eye out for requests for help that might be coming through in the next couple of weeks, because there is a lot of prep to help out with leading up to the test and then on the actual day of the test itself. And we're hoping to have one of these towards the end of October to test the new printed nozzle. So I'm going to switch gears now and talk about our software systems. And similar to electrical and infrastructure, there isn't really one specific module on the rocket that the software subteam is responsible for. We have a bunch of different pieces of software, both on the rocket, off the rocket, and some that aren't even really related to our technical development at all. And the software team is responsible for working on all of these projects and just making sure that everyone who wants to write code gets the reviews and the help that they need. In terms of our software systems, we have a couple main onboard systems, and in most cases, there's a lot of collaboration between the software team and the electrical team when we're working on these, because the electrical team, or in some cases the payload team, is responsible for designing and building the hardware that the code will actually run on. So there's a lot of overlap between our teams. Most of the people who work on the onboard electrical systems are both on the electrical and software subteams, and they do a lot of the electrical design as well as the coding. But there are definitely people who just prefer to do one or the other. Our main onboard electrical systems are rocket can and payload, which Shirley mentioned earlier. And then in terms of offboard electrical systems, we have RLCS, that's our launch control system, data acquisition, DAQ, as well as a system called St. Pat's, which is basically a transponder for helping us find our rocket, which we're not going to touch on a ton here. Software team also does work on a lot of code that isn't directly related to launching the rocket itself. Code that doesn't run on any of our launch systems or on the rocket. It's mainly for simulating, modeling, or doing some sort of calculations to help us in our design and testing. There are too many of those to list, but I'm just going to touch on a couple. The first one is Open Thrust, and that's a simulator that we use to simulate our engine. So I mentioned earlier that engine tests are very resource intensive. And so while they're a great way to find out more about our engine, we don't want to have to run a full test whenever we want to make a very small change to the engine, like changing the amount of propellant that we have or making a change to the injector. Open Thrust is a piece of software that we are developing to help us simulate that. So we can just change the parameters of the engine in a configuration file, rerun the software, and it will tell us how the performance of our engine will change. And we can only get so close in modeling this because engines are really complicated. But our hope is that this will provide us with a good approximation of how changing different parameters affects the engine performance. And this will let us make changes to our design without needing to run a ton of tests. The other big project is Topside. Topside is a simulator for simulating our pre-launch operations. So there's a lot of steps that we need to go through in order to actually launch our rocket. We need to load all of our propellant on board. We need to make sure that the area is safe and secure. And then finally, we need to actually ignite the engine. And that can get really complicated when we're working with two different propellants, when we're trying to do it all from 2,000 feet away to be as safe as possible. And our procedures have got really complicated over the years. And Topside is a tool that we're developing to help us, again, simulate what will happen if we run a certain procedure, and let us visualize that and sort of develop a bit more intuition about how our system works and how we should design our procedures to be as safe as possible. Last on the list here, we have a few projects that we also manage that aren't related to our technical work at all, but are more on the organizational administrative side. The two main ones, Minerva, which is our custom Slack bot, Essentially, she manages meetings on our calendar, sends meeting reminders, handles the agenda, just helps us work a bit more efficiently. And finally, the website, which we periodically update with new team members as people join, as well as new sponsors as we secure them. And that's it for software. Well, that's not it for software. That's all that I have time to talk about for software. Finally, I want to talk a bit about some of the non-technical teams that we have. The first one that I'm going to talk about is our business team, or sponsorship and finances. Rockets are not cheap. On average, for a full development cycle over the course of one competition year, we spend upwards of $10,000 just on R&D, and that doesn't include everything that we need to spend as well for competition expenses, administrative. So we do need we do have people that put a ton of time and effort into securing funding for the team, both from within the university, but also reaching out to corporate sponsors and hopefully getting either parts donated or just direct monetary sponsorship. And this is a really important team. And without funding, we can't really do anything. We wouldn't be able to build rockets that are as cool as we have. And a question that I get a lot is, can I work on sponsorship and finances and also work on a technical team? And the answer is absolutely. It's actually really beneficial for people to have an understanding of the technical side in order to work on the sponsorship side, because when we're reaching out to sponsors or putting in proposals for funding, we need to be able to talk about what we're actually going to use the funding for and really understand what it is that we're going to want to spend it on, or what part we need and why. So working on a technical project is really helpful when you're reaching out to sponsors. And conversely, working on the sponsorship side is also great if you want to gain an understanding of all of the technical projects that we've got going on, because that's something that you'll develop as you're putting together those proposals and reaching out to sponsors. That's all from me. You're muted.
I am muted. So thank you. The next kind of sub-team we'll be talking about is media and outreach. So our team loves taking pictures, making videos, and reaching out to the community. We have a Flickr account with over 1 million views on it and thousands of pictures. If anybody's interested. In the past, we've held many outreach events. Any outreach event is kind of just unrelated to our mission of building the rocket and reaching out, giving back to the community. So we have done high school presentations in the past around the Kitchener-Waterloo area, where we've brought some hardware over, some of our actual rocket hardware, and talked to high school students about STEM and rocketry in general. We have an event called Aviation Fun Day. We also have the annual event called Rocket Drag Race, which we weren't able to hold this year because of the pandemic, but we gather all the first years and they build their own model rockets, they paint it, and we give out prizes accordingly. So we love outreach, we love media. If you're into photography or any kind of graphic design, or if you want to learn, then this is a great opportunity. We have an upcoming static fire that we'll definitely be taking a lot of pictures of. So if you're interested at all in this kind of stuff, then there's definitely room for you. Next slide, please. So a lot of first years may be wondering, I just got to university, I haven't really learned anything in my courses, I have no experience whatsoever, will I even be able to do anything for the team? And the answer is yes. So listed on the screen now, you can see to the right a picture of all the previous first years from the class of that joined last year. And on the left is a list of just some of the things that they've done. So we've had field sensing, prototyping, and testing, software design and development for Topside and Minerva, which Jacob touched on earlier, electrical design for GPS, live telemetry, and the RLCS, our remote launch control system, payload research and experimental design, and mechanical design for the recovery team. So just because you're a first year doesn't mean that you can't do anything. In fact, there's really no kind of like, your year is kind of irrelevant for us. Next slide, please. So on the topic of first years, today, a big question that we also get is, how do you get involved? You know, you just joined a team, but you're kind of lost on how to to take your next steps. Now, the first thing you should do is join our Slack. Slack is a software that allows us to communicate, and it's where primarily all of our communication is done. So if you visit waterlooorocketry.com/join, there is a sign-up form where you can give us your contact info. Don't worry, it's not an application process. It's just for us to get your contact info so we can invite you to our Slack workspace. Also, the team gathers every week at Thursday, 7:30 p.m., and the meeting usually lasts about an hour to 8:30 p.m. This is just a general meeting for all the sub-teams to touch base. On top of that, each given sub-team has their own meetings throughout the week. Now, this timing varies between sub-teams, and it's unrelated to the weekly general meeting. And I also will say here that just because you're on one sub-team doesn't mean you're locked into that sub-team. You can be on as many sub-teams as you want or as few as you want. But yeah, each sub-team has their own meetings throughout the week. And even though we're in the middle of a pandemic and we're not all on campus, remotely, there's still a lot of work to do, maybe even more work to do. So don't worry about that you came to university at such an unfortunate time. Next slide. So I'll hand it off to Roman to conclude the presentation.
Yeah, absolutely. We'll be concluding the formal part of our presentation. Want to say thank you so much to all you guys for watching. Want to say thank you to all of our sponsors as well. Yeah, so I mean, you can see these are some of the companies that support us. Jacob touched on the importance of sponsorship. These are the companies that actually kind of either give us money or material that we request from them to build our rocket. The team's also a good opportunity to get exposure to the industry, to get better co-op opportunities, and to learn about different aerospace companies and things that do companies that do things that you're interested in. So let's go to our general Q&A session. As you saw, or as you see there on the bottom right, you can ask your questions anonymously on Slido, the room code WR-info, and I see that we do have a bunch of questions posted on our board here. Let's begin. Let's pick the first question. Do I need to have prior knowledge about rocketry or rocket building? Absolutely, you do not need to have prior knowledge about rocketry or rocket building. I mean, none of us did when we joined the team. You come to university to learn about all this stuff, so never fear. Don't think that you can't join the team because you didn't understand what half of our presentation meant. I mean, I didn't understand what half the presentation meant when I joined 2 years ago. Yeah, absolutely. You're coming to this team so that you can learn, so that we can teach you, and so that you can do interesting stuff. I'm not in Mech-Tron, CS, SC. Does that mean that I'll have fewer opportunities to do stuff, especially if I'm interested in those disciplines? Well, absolutely not. If you're interested in those disciplines, then you can join any project that's related to that. The only advantage that that you don't have is that some of your course content maybe isn't covering those topics in such detail, but absolutely, as I said, you're coming to the team to learn about the projects that interest you. So,
Hey, Roman.
Yeah, absolutely, Shirley.
Do you mind if I just quickly give some examples?
Oh, yeah, sure.
Just to give you an idea of what a range of programs we have on our team. We have people in physics. We have someone in AFM. In math. We have various engineering programs. Chem-Eng. We've had people in civil in the past. In addition to in addition to the ones that you just listed. So absolutely not. It does not limit you. It might affect what you're interested in. Generally, people try to work on things that are relevant to their programs, but it really doesn't limit you in any way.
Yeah, and if you're interested in working on a project, but you're not sure if you're not sure if you have the background or if you'll really be exposed to a lot of the relevant content in your courses, then that's totally okay. Just let us know, and we've all been there as well. We can point you towards some resources that will help you out, and we can definitely guide you through that process as well. We're here to facilitate your learning and help you out regardless of what you want to work on.
Yeah, and yeah, absolutely, that's all true. Next question. I'm actually going to go to this one for you, Jacob, because you've been handling a lot of it. What does training look like for first years and new members? Where can they get that information?
Yeah, that's a great question. The answer is it depends. If you're So it really depends on what sub team or sub teams plural you decide to join, and what projects you're interested on working on. There is, in order to join the team and get started contributing and helping out with a project, we don't have any minimum like training course that you need to complete before you can be actually considered a member. There is some safety training that you will need to complete if you want to work in the bay or help out with any of our engine tests, but that's not required in order to join the Slack and start helping out with design and coming to meetings. In terms of technical training that you might find helpful or useful in order to get up to speed with some of the projects that we're working on, again, that's highly sub-team dependent. On the software side, we point you towards resources for learning Git. We also have a big document of sort of software best practices and pitfalls that you can fall into. On the electrical side, there are tutorials for electrical design, for designing circuits and printed circuit boards. And we can also, if you're in Waterloo and you want to help out with some of the electrical assembly, then we can train you. We can teach you how to solder, how to crimp connectors, and just other electrical assembly tasks. On the mechanical side, I think Roman or Shirley, you guys can probably talk a bit about that.
Yeah, absolutely. I mean, I'm also going to kind of tag team and answer another question, which is asking, how do I get involved after joining Slack and attending this presentation? It also goes along with that previous question. Is if you're interested in a project, in any project at all, message the person that's leading it and let them know you're involved, and they'll usually send you some resources to get started. It kind of varies project on project, depending on what's actually involved. You know, the kind of prior knowledge that you'll need to, you know, if there's any kind of required reading or anything to touch up on. For example, for the recovery team, there's a couple of articles that I'll send you. There's a previous, our previous team reports are also a fantastic way to get prior knowledge and to kind of get going, to get more information about the team, to get more information about our systems. And also, yeah, so with the recovery specifically, I mean, we wrote a little report about last year's recovery project, so I'll send you that to you as well. Surely you can speak to some Airframe and maybe.
Yeah, I was more talking about the mechanical onboarding and sort of CAD tutorials that you guys have been working on.
Oh yeah, absolutely, sure. Yeah, Shirley can definitely cover that.
Yeah. So we are currently working on some hopefully interesting content for the more mech side of onboarding. So we have some tutorials planned in terms of getting you guys up to speed on everything related to CAD, computer aided design, 3D modeling using SolidWorks, and introductory like solid mechanics, just to help you guys get up to speed and get the basic skills you need to start working on more interesting projects. So yeah, keep an eye out for that. We will be posting this information both on Slack as well as our Facebook group.
All right. Yeah, awesome. Absolutely. Next couple of questions revolve around whether you have to be in Waterloo. Are there going to be any in-person meetings? Do I need to be in Waterloo to work on projects for the team? Any of you guys want to speak to that?
Yeah. So first question: are there going to be any in-person meetings in Waterloo? Maybe. We will not be holding any of our general team meetings or our weekly sub team meetings physically in Waterloo just because of where everyone is located, and in order to be safe and maintain physical distancing. So we won't be doing any of that this term, possibly next term as well, depending on how things shape up. So if you're not physically in Waterloo, you won't miss out on any of the sub team meetings or general team meetings. Those will all be held over the Jitsi platform. Do I need to be in Waterloo in order to work on projects for the team? Absolutely not. Most of us are remote. I'm remote. Shirley's remote. I think, Ryan, are you remote as well? Yeah, Ryan's remote. A lot of our team is working remotely now, whether we're on co-op or school terms. There is a lot to do right now in terms of design and research and analysis. There is a lot to do in terms of manufacturing and prototyping and testing as well. So if you are in Waterloo and interested in working on that, then let us know. But you definitely don't need to be in Waterloo in order to work on projects. Most of us aren't right now.
Yeah, awesome. And maybe you can also talk about how many hours per week do we need to commit. We don't have any specific requirement for how many hours a week. It's however many you need. And obviously, we understand that school and life comes first, before design team. This is after all an extracurricular. But you give as much as you can, and I mean, ultimately you're in it to learn, and you're in it to get what you came here for. So. If you take on a project, just make sure you're communicating with your project lead if you feel that you're unable to do what's required for it.
Yeah, and you can definitely, especially in the beginning, if you think the team is kind of cool and you're interested in learning more about what we do, but you're not sure yet whether you want to commit and take on a ton of work, it's totally okay for you to just come to our meetings, listen in, ask questions if you want, but not take on any work. That's totally okay. If you want to do that and sort of feel it out, get a sense for how well you can balance school and a design team before you actually commit to something hard, then that's definitely okay. We won't assign you anything unless you're ready for it and you ask for it. So just let us know if you're interested in taking on work, or if you feel like you're at a stage where you can handle it and take on some more work in addition to your class load. And yeah, we're all flexible. It's the same for all of us. Some of us will take on more of a time commitment during easier terms, lighter terms, and maybe sometimes in more difficult terms we won't do really much for the team at all because we want to focus on school. And so that's something that's just an understanding for all members of the team, that we don't require any time commitment, and we just expect people to be open about communication and not promising to take on things that they don't have time for. But yeah, communication is the key here. Just let us know what you think that you can do, and we'll based on that we'll make sure to give you work that you both find rewarding and isn't too much of a too stressful for you based on your workload.
Very good. Another question here from Slidu is, can you be on more than one sub-team? I think we touched on this in the presentation. Absolutely you can. You work on whatever's interesting. Just keep in mind that sub-teams do have their own meetings at various times throughout the week, so you should be attending the sub-team meetings for whatever projects you're involved in. Another question here. I feel like working on complex projects can be a bit out of my league. How do other students help us with overcoming that? So I'm gonna say for starters, that's part of the onboarding process. We definitely do try to communicate as much as the kind of required startup information through our onboarding tutorials and through all of our resources. What else? Shirley or Jacob or Ryan, do you want to speak to that? Anything to add?
Yeah, I'll just add on to that. even though yes, building a rocket and testing it and launching it is a very complicated project, we do our best to break that down into smaller pieces in terms of subteams, some subsystems, and then we break those down even further to smaller projects that when you look at them, a lot of them really aren't that complicated. And we will definitely when you join the team. We will definitely not sort of throw you on and say, here, redesign the entire recovery system, unless you're Roman.
Yeah, it's actually a
So
project I got last year.
so we won't do that. We won't do that for new members. If you don't feel you're comfortable with the level of complexity, our sub team leads do like we all do our best to make sure that that for the projects we're responsible for, we can break those down into smaller pieces that are like good first issues for people to jump on, good starting points that aren't so complicated and don't require a ton of background knowledge, and can be finished a bit more quickly, so that you don't need to go way deep into a project that'll span several months and you might not see it through to completion. Definitely not. We make sure to give our newer members projects that they'll be able to complete a bit more quickly, and that they won't have that won't be too complicated for them based on what you guys are comfortable with. So just let us know if you feel like something is too complicated and you want help. Then that's what we're here for. We can always help you out, and we can always work together with you if there's something that you feel you need help with.
All right. Yeah. Thank you, Jacob. And yeah. So just two last quick questions here on the Slido, and we'll be moving on to the breakout rooms. If you have more questions, feel free to put them, or feel free to ask them in those breakout rooms. You'll be able to chat in voice or in text if you'd like to. Actually, one-on-one to current members, so they'll be able to answer a lot more questions. So the two questions here are how can one join specific sub-team meetings? Like when do they meet? How do you get the link, invite to the meeting? So the platform that we're using for all of our meetings is on Jitsi, and it's actually all going to be in the same channel, just meeting at different times. The way that you can figure out when they actually meet is by subscribing kind of to our Google Calendar, which you'll be able to get access to, once you join our Slack. I believe it's either pinned in the general channel, or just ask to get access to it, and then you'll be able to. Sorry, is it?
It's also in the team. It's also in the team manual.
Oh, right on. Okay, so yeah, so it'll be right in there. You'll just be able to request access to it to see when all the meetings are. You can jump into any meeting that you'd like to just by using that Jitsi meeting link that we use. And then how can I become a full member of the Slack? See all the channels.
I think I can probably answer that.
Sure, Shirley.
Yeah, so essentially, Slack allows us to bring on guests at no costs. But those guests can only see one public channel at a time. They are free to move around if they ask an admin, and we're very happy to move you guys to whichever channels you guys are interested in. But in order to see all the channels, there is a yearly fee that full members have to pay, and we don't want to ask you guys to commit to that cost until you're really sure that you want to join the team. And there are a few other like training and other considerations, but essentially it'll probably be around a few months, roughly. But yeah, feel free to talk to any one of us or someone that on Slack is an admin, and we'll be able to move you guys to whichever channel you like.
All right. Yeah. All right. Thank you, Shirley, and thanks everybody. We're done the main Q&A session, but now we're actually gonna go on to our breakout sessions. So I have two links here. One is for people that are interested in talking about more mechanical topics and kind of general team topics, and one's for people that are interested in talking about more electrical and software. Feel free to jump around. And there are also going to be two specific Slido rooms that are associated with, or sorry, Slido like question rooms that are associated with both of these chats. So if you prefer to ask your questions anonymously, you'll be able to do that, and the team members inside of those Jitsi meeting rooms will answer those questions. Thank you all for coming to the Waterloo Rocketry Fall 2020 info session. We look forward to seeing you on our team. Remember, it's waterloorocketry.com/join if you'd like to get added to our Slack channel and get involved with the team. Hope that you've enjoyed. Hope you learned a lot. And yeah, we look forward to seeing you guys on the team.
All right, I'll see you guys in the mechanical call.
I'll be over in the software and electrical one if people want to join that one.
Yeah, absolutely. And
Should we message the channels with the links?
Yeah, with the Slido links.
Awesome. Yeah. So I'm actually gonna swap over the overlay now. Just gonna put up gonna leave up this page and gonna put up those Slido links. So thank you guys so much for attending, and we'll see you guys